We have discussed the Raft consistency algorithm and TiKV's RocksDB underpinnings. Next, we will discuss how TiKV data is written. The process is as follows. Let's say we want to write key equal 100, value equals Jack. TiDB server asks the PD where the region containing key 100 is located. PD tells the leader on which TiKV node the region is located. Next, TiDB server sends the write command to the TiKV node where the leader is located. And then, after the leader node accepts the write command, it starts the TiKV write process. Here we use two components, one called Raft store pool and the other one called apply pool, both of which are mechanisms used to write to the RocksDB persistent storage engine. Recall, there are two RocksDB instances in each TiKV node. One instance is responsible for persisting Raft logs. We call this one RocksDB Raft. The other RocksDB instance is responsible for persisting the real key value pair data. We call this one RocksDB KV. When the leader node receives the write command, the Raft store pool serializes it into a Raft log and submits it to the RocksDB Raft for persistence, and this is an append. At the same time, the Raft store pool is also responsible for distributing the Raft log to the TiKV nodes. This is replicate processing, where the followers are located. When the majority of followers in the cluster receive this Raft log, it is considered committed. Next, the apply pool parse the committed Raft log, that is the Raft log, and applies it to the RocksDB KV instance. The leader then applies key equals 100, value equals Jack to the KV RocksDB and returns write success to the client. After that, our client's commit succeeds and other sessions can read this data. When it comes to reading, TiKV first needs to guarantee linear consistency. For example, at 10 o'clock a.m., we change key equal 1, value equal Tom to key equal 1, value equal Jack, and commit. So that is, after 10 o'clock a.m., we can't read key equals 1, value equals Tom. Here, let's first discuss the situation of reading from a leader. Let's take a look at a simplified process first. Assuming we want to read key equals 1, first, the client asks PD about the region where key 1 is located. 2, PD informs the leader where the region is located on which TiKV node. And 3, TiDB server sends a read command to the TiKV node where the leader is located. 4, the leader node accepts the read command, reads the RocksDB KV, and returns the data to the client. The only problem we need to solve at this point is when we confirm the leader, which is step 2, until we read it, step 4, we can ensure that the node is still the leader without switching the leader role during this process. The so-called read index read solves this problem. Let's take a look at the specific process. 1. When TiKV receives a read request, it records the current log, that is current Raft log, sequence number, also called commit index, into a variable called read index. 2. After that, this node initiates a heartbeat to the other nodes. If most nodes return the corresponding heartbeat response, that is a heartbeat response, then the reader can be sure that there is still a leader. On the other hand, we believe that the node at that point is no longer the leader and needs to be reread by the TiDB server. 3. If you confirm that the current node is the leader, wait for the Raft log to be applied until the sequence number of the log, that is the apply index, exceeds the read index, so that consistency reads can be safely provided. Then 4. Reread the RocksDB of the leader node and return the results to TiDB server. Here we have introduced read index read, and the follower read function that we will explain later is also implemented with it. You can see that unlike reading through the Raft log, read index read uses heartbeats to make the leader confirm its state, which is much easier. Although there's still network overhead for the heartbeats, the performance is better than the Raft read log. From the previous slide, we learned that when a read request reaches the current node, the node needs to initiate a heartbeat to other nodes. If most nodes return the corresponding heartbeat response, then the leader can be sure that it is still the leader. This step requires network overhead. While the cost of a single heartbeat is low, an increase in the number of heartbeats can slow down operations. Previously, we introduced a concept called Raft leader election, which is the heartbeat time interval. Remember, the leader sends a heartbeat, which requires a heartbeat time interval to be less than a minimum election timeout value. Stated another way, the leader will send a heartbeat every heartbeat time interval. We record this time point as start. If the majority of followers give a heartbeat response, followers will not initiate re-election until the election timeout period. So, even if an election occurs, the new leader will be elected during election timeout clock drift boundary. We call this period a lease, or a lease period. Well, within a lease, the node does not need to issue a heartbeat to determine that it is still the leader node. In this way, we no longer need to send a heartbeat to determine if we currently are the leader. This improves efficiency. Now we have 2 points that we need to be aware of. One, the CPU clock time of each TiKV server is accurate, and the error should not be too large. If the clock frequency of each server is different, there will be problems with the lease mechanism. If this is the case, we can also use read index read. 2, TiKV doesn't actually update the lease through heartbeat, but writes. Since the Raft log is sent once for any write operation, we record the current timestamp start when we initiate the write request, and then wait until the corresponding request is applied so that we can renew the lease of the leader. The read and write operations introduced earlier are all performed by the leader node. So this naturally led to the idea that the follower node can share some of the reading pressure. This is called follower read, and here's how it works. 1. When the TiDB server sends a read request to a follower node, the follower needs to ask the leader node for the commit index of the Raft log of the current latest commit. 2. The leader node informs the follower node of the current commit index. If the follower finds that it does not have a Raft log with the sequence number applied, it will wait. And 3. It will wait until the follower confirms that it has applied locally to the commit index just sent by the leader. The follower and leader are synchronized and the data is read into TiDB server. So far, TiKV has solved the problem of data storage. So currently the entire TiDB database can be processed as shown in the diagram. Recall, TiDB is stateless and the data is stored in the TiKV layer. When TiDB receives a query request from the client, it gets the data from TiKV. In this diagram, what will happen is, or what's implied is, that all the data will be returned into the TiDB server and the count performed there. That's what we're trying to get to. So there are 2 performance issues with this architecture. TiKV returned all the data and the network is too expensive, so lots of network traffic moving all the data up from TiKV into TiDB server. And 2, TiDB server needs to process all the data. This would consume a lot of CPU. Meanwhile, TiKV only needs to read the data and pass it along to the TiDB server. This means TiKV has very low CPU utilization. Fortunately, this isn't the way it actually works, and we have the coprocessor to thank for fixing this. Notice that we have a new box named coprocessor added to each of our TiKV nodes. The coprocessor empowers TiDB database to push the SQL execution down to TiKV. Another way to say this is we have pushed the processing down to the data. Here is a generalized coprocessor workflow. 1. TiDB server receives a query statement, analyzes the statement, calculates the physical execution plan, and then breaks down the TiKV coprocessor request. The TiDB server optimizer knows exactly what the coprocessor can do. Next, TiDB server distributes the coprocessor request to all relevant TiKV nodes according to the distribution of the data. After the TiKV server receives the coprocessor request, it filters and aggregates the data according to the request operator, and then returns the data to TiDB server. Keep in mind, the data returned to TiDB server is much less than our previous diagram. In this case, each node could send an individual integer to TiDB server. That's a simplification, but you get the idea. Remember, we're doing a count star, which each node is going to count the information on itself. Finally, after receiving the returned results of all data, TiDB server performs a secondary aggregation, calculates the final results, and returns it to the client. In this case, TiDB server is adding up some integers because we're doing a count star and is not going through all the data. There are currently 3 types of requests processed by TiKV coprocessor. The first is a directed acyclic graph. It executes the physical operators to calculate intermediate results of SQL, thereby reducing the computation and network overhead of TiDB. This is a task performed by the coprocessor in most scenarios. The physical operators currently pushed down include table scan, index scan, selection, which is another way of saying column filtering, limit, top in, aggregation, and others. Next, it can push down analyze statements, which analyze table data, statistics, and it samples table data information. This is used by TiDB's optimizer. And finally, checksum. Checks the table data for consistency after importing data to make sure it's correct. So let's close out this coprocessor discussion by showing something I mentioned earlier, and that is that we're doing a count star from a table. Each coprocessor is going through and doing its individual counts and returning them back to the TiDB server. So we can see that each TiKV node returned an integer of 3, and then TiDB server will go add those up, come up with 9, and then send 9 back to the user. We've covered a lot of material during this module. I feel confident that we've met all of the objectives defined at the start. We can describe the structure and function of TiKV. We can describe TiKV's principle of persistent data reading. We can describe TiKV's support for distributed transactions and MVCC. We can describe TiKV's distributed consistency guarantee based on the Raft algorithm, and we can describe TiKV's coprocessor capabilities. Thank you for taking the time to view this module. We hope you enjoyed it and learned a lot.